see it counting down now, but do y'all still see the PowerPoint here? Yes?
I do.
Okay.
Yes, sir.
Now what I'm going to do, I'm going to lose this for a moment, because what I'm going to do is go back and get Blackboard up, so everybody can see Blackboard, because several of you are here for the first time and I want you to do it. Now, if you see someone else trying to get in the room, let me know, because I don't want to lose anybody. So let me get Blackboard started. It's a long and stupid process we have to go through to get that, but I'm on the way to doing that now. Okay, here comes somebody. David Whitlock, I guess, went out and came back in. Okay, if y'all see David show up, tell him I'm in the process of getting Blackboard started. Okay, because we still have.
Now,
say again?
Now, we hit mute does or us.
What do you say?
If I hit mute.
If you hit mute, then I can't hear you anymore.
Okay.
I think you always hear me. You can't get out of that. But okay. All right. I'm going to pull up Blackboard, and then as soon as it comes up, I've got to log in, and this takes a few minutes. It's a weird login if you are familiar with it, because it won't all fit on the screen at the same time. Okay, we're almost there. All right. Okay, this is Physical Science 111 summer term. I have a last spring term as well, so if you ever are missing anything, it might be that I screwed up and put it in the wrong class, but don't try not to do that. Okay. Now, obviously, you all saw the announcement because you got into Blackboard. You got into the Zoom. So glad you managed that one. Here's the course content. Now, I'm not going over everything, but here it is. And one reason oh wait, you can't see it. Let me get this new share, and I think it's this one. Okay. Can you see my Blackboard page here?
Yes.
Yes.
Sir.
Okay. So y'all can go to the syllabus and read what's in the syllabus. Now, I'm not going to go over it, but I'll show you how to do it. On this page, okay, there's several different icons here. This one represents a document, like the syllabus, my locator card, research paper instruction. This is a link. We'll get to the link in just a minute. This is a folder. Okay, now these things open differently, and I'm going to show you how to open these. Are y'all familiar with this? Do I need to go over this?
No, I am.
You are? Okay. Is anyone not familiar with how to operate this? I can't hear.
Yes.
Is everybody saying yes, or some people say you need to see it? Yes. Okay. So I won't go over that. So there's the syllabus. You know how to get to it. There's the locator card that shows when I'm in class, not in class, whatever, in the office, not at the office. Also has about when I'm advising and not advising, though most of the time, even when it says advising, I won't be, because there's not that many anymore. Here's your research paper instructions. That's something that's coming up. Don't forget this. Here is a YouTube video. This is the one I wanted to do. This is a link. All you have to do here is click on the link, and it opens. Can y'all see this table or listing scroll of thing? This is the old stuff I did last term or a previous term. The new stuff is at the bottom. So I'm going to scroll down to the bottom. This one down here that says Physical Science 111 syllabus, This is what we did last time. So for those 4 or 5, however many of you are new this time, it looks like 4, this is where you go back and see and hear, because this is a YouTube video. This is from the Screencast-O-Matic. Everything that we said was recorded on here. I talked about the syllabus. I talked about the locator card. I talked about the research paper instruction. I talked about Blackboard. I talked about it all. There you can see it. Also, we got started in chapter 14. So you can pick up to where we are now. We started in chapter 14 on page 353, and we're now on 360. So there were 7 pages we covered. You can go over that there. Okay? You can find out about the book. You can find out about all sorts of things there on this YouTube video. That's why I wanted to show this. Okay? How you get to it. That's how you can catch up from what we did last time. Okay, I'm going to close this for now. Now, some of these others, this Hubble Pictures, that's a folder. And again, you said you understood this. Trouble is, Parisha's in the way, isn't she always? Okay, see if I can get, okay, here, that's out of the way now. Okay, here we go. You can click on this arrow over here on, oh, wait, David Whitlock's coming back in, so let me get him back in. Was someone going to say something? Okay, I thought someone interrupted. Okay. When you want to look at something in a folder, you can open the folder over here, and then these are your different pictures off the Hubble Space Telescope. There's 10 of them. They're just really pretty pictures. Nothing really to do with them. They're just really pretty pictures. Okay? I'm going to go back here and close that. All right. Here's another document, Space Objects in Perspective. I found that a really interesting little document to look at. You can look at that. Here are our PowerPoints. Every PowerPoint will possibly do this term. And that, again, is in a folder. So you can open the folder, and there's Chapter 14 PowerPoint, 15, 16, 17, all those. Okay. Now, for those who were here last time, you may notice here is a new object in my content. This we'll be using in the lab today. So for those who were here last time, you haven't seen this. We'll wait and open it until we get ready for lab. But for right now, just to let you know, I did put this in. Now, did anyone also notice, now what I'm going to do here, and I think all of you are familiar with Blackboard, okay, you see this little icon here on the messages. Did anyone look at messages since last night?
I did.
If you did, you'll notice I put the lab out there. Oh, some people have responded too, I guess. Okay, and but here's what I put in there. There is it's Physical Science 111 Lab 1. That's what that stands for. And this is a PowerPoint, a WordPerfect a Word document that you can open. And in fact, I would say get it open. And that's what we're going to be doing the lab on. So if you can print it. Or if you want to open it and just work on it when it gets lab time, that's where you find it. It's under Messages. That's the only place where I can send attachments. Okay? You can also send things back to me through Messages, or you can copy them and do them on email. Either way. And I don't know who Scott Lucas is. He is in the class, but he hasn't shown up yet. He's saying he's won't be back until someday in the future. I can't see the message here, but let me see. Until Wednesday. So he'll be in on Wednesday. Okay. I hadn't seen that until now. So there are Messages, and we'll come back to those when it's time to do the lab. All right. So do you new folks feel at least that you can catch up? You know how to do that now, all right? Now I'm going back to my PowerPoint. And we'll go from the current slide. Now, last time we went through a lot of stuff, and we went through it fairly quickly. Did any of you have any questions before we start back where we left off last time? None? Okay. So we're on, by the way, all right. We had actually stopped at an example here, and I'm not going to do many of the examples because they require you to use formulas that you probably are not that familiar with. This is assuming you've already had Physical Science 112, which in Alabama they do Physical Science 111 first most of the time, and that's Astronomy and Earth Sciences, and then do Physics and Chemistry second because they think they're harder. But Astronomy and Earth Science depend on Physics and Chemistry, so the book assumes you've already had Physics and Chemistry. Most of you have not. So that's why I have to skip most of the examples. But it's just an example. Now, in my last class, they had me do this, and this is admittedly really, really awkward. But I'm going to do it for you because the last class made me do it. Can you see the whiteboard here? You see it with
Yes,
a pen?
sir.
Okay. Now, here is the formula that whiteboard is using. We were just talking about star temperatures, and here's the formula, and I'm going to try to write it with my pad here, and it is terrible. I'll admit that in the first to begin with. So here is the formula. That's supposed to be a capital T. Capital T stands for temperature. And that temperature is equal to a big old number here, 2.897. My writing is really terrible when I'm using a pen. When I'm using my finger, it's even worse. Okay? 897. Okay? Times 10. Now, in the book, if you're on page 360, they left off the exponent here. Okay? Times 10. Okay? Raised to the 7th power. They left off the 7. So if you've got a book, write that 7 in there. Okay? Now that number there, 2.87 times 10 to the 7th, has units of Kelvin. That's a temperature measure, absolute temperature, times angstroms. Okay, now I don't want to spell out the word angstrom. Here is the symbol for angstrom. It's a capital A named after somebody who could be a potential paper topic, but they put a little circle over that A so you don't confuse it with amperes or something else. Kelvin is named after somebody too. That's why it's a capital letter there. It's not his name, it's actually his title. That was Lord Kelvin. His name was William Thomson. Okay? He's a potential paper topic as well, if you want to write on him. And this is divided by the wavelength, and that's supposed to be a lambda. That's about the ugliest lambda I've ever seen in my life. It looks like a skinny man praying or something. I don't know what he's doing. Okay, and this is called the peak wavelength. So I'm just going to put it P here. In the book, they spell out peak. Since it's so hard to write on here, I'm just going to call it that. That's your equation 14.2, okay? Example 14.4 says what is the temperature, so we're looking for temperature, capital T, of a star emitting light with a peak wavelength. That peak wavelength is going to be 3,500 angstroms. So what we're going to do is set this equal to that number on top, 2 point, that's supposed to be a decimal point. This is terrible, folks. Let me see if I can erase. Earlier today, the eraser and nothing would work for me anymore. So I had to bring it down and start over again. Hopefully that won't happen. That is not a comma, that's a period. Let me go and erase that too, so it's easier to read. Okay. Go back to the drawing. Okay, let's see if I can get the period. There's a period. That's a really little one. 2.87. And see, it does things like that. I did not do, it did it on its own. And I don't know if the eraser is just going to erase that piece or it's going to erase the whole thing. Well, erase more of it. Okay, first I got to admit someone back in the room. Can anyone see who that was? Because I can't see, it's blacking me out. I don't know why it does that. Who just came in? Can you tell? Can anyone tell? Okay, let me see. Should have 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, must be someone who had to go out and come back in because I don't think it's anyone new. Okay, this is terribly painful watching me write this, I know. So let me get my drawing back. Okay, that's supposed to be 2.897, so I'm going to try to put the top on the 8. 9, 7 times 10 to the 7th and that's going to be Kelvin angstroms. Kelvin is a temperature measure. That's a capital K. It doesn't look like it, but it is. Angstroms, that's a length measurement. It's not used that much anymore, but this book is using it here. It has a little circle over it. And divided by, and it said the peak, this star has a peak wavelength of 3,500 angstroms. So it's 3,000, and this is a comma there, 500 angstroms. This is terrible writing, I admit. All right. Now, the reason I put units in is to show you that the angstroms actually cancel out. This cancels out that. One's in the numerator, one in the denominator. So you're going to be left with so many K, Kelvin. That's the temperature. All right, now I'm going to get my calculator. It's my telephone. I've got to log in. Okay, pull up my calculator. There it is. Now I'm using scientific notation, so I'm going to turn it sideways to get scientific notation. You see it? Okay, that's the big scientific calculator. Okay, so I type in 2.89, oops, 8 didn't register, 2.897. Okay, I type in those digits, you see. Now, how do I do times 10? Don't do a time sign. Don't do a 10. What you do for that scientific notation, you see this key right here that says EE. That EE key is your scientific notation. So 2.897, then you press the EE key. Okay, you see it lightened up there. And then you type in 7. Now, all you see is a 7, and you're going to take that and divide it by pressing the division. Now, this just wrote that not in scientific notation. 28,970,000, that is what 2.897 times 10 to the 7th is.
You're going out, Professor. You're going out. We couldn't hear you.
Okay. The reason is I found out in the last class my microphone is with the camera. Okay? So if I show you something with on the camera, I block my voice. Okay? So I'll try to talk around it. Can you hear me now?
Perfect.
Okay, good. Okay. I sound like a Sprint commercial, though. Never mind. Okay, we divided that by 3,500. 3,500, okay? Divide it by 3,500, okay? and then press equal. And that gives us 8,277 K. You see, your units that's left over is K. So this is equal to, all right, this is equal to 8,000. Now, here's a little bit of an issue here. Wait, here's someone in the waiting room. David Whitlock is trying to come back in. Guess he's having trouble staying in, but I'm glad he's here and trying to get back. Okay, now I'm going to write down all those digits for right now. Okay, that's 8,277. Now my calculator actually shows more digits than that, but I'm going to stop it right there. 277 K. All right. Now I'm going to show you something that the book does most of the time. Hopefully it still does. The reason I stopped it there, notice the next digit after the that second 7. I'm trying to get out of the glare. Okay, that digit after that's a 1. 1's less than 5, so I throw it away.
Going out. You're going out. I'm sorry, we can't hear you.
Okay, it's because I've got the calculator in front of me. Okay, can you hear this?
Still can't hear you.
Still can't hear me. How about this? Can you hear this?
No, we see the screen, but we can't hear you.
Okay, how about this?
A little bit better.
A little bit better. Okay, let me try talking on this side of it. Okay, can you hear that?
Oh, no.
No, you can't hear at all.
We still can't hear.
Okay. If I hold the calculator in front of the camera, then it's in front of the speaker as well. So I'll say what I'm going to say here. Notice the digit after the 7 is a 1. Since it's less than 5, we just drop it. So that's why I stopped at 8,277. Okay? However, notice here, we have 4 significant digits there. You can't hear me?
No.
Okay, can you hear this?
Yeah, I can hear that, but when you get your phone up, that's what
Okay, well, I didn't have the phone in front of me then, so it may be my sound's going in and out. We have 4 significant digits here, but down here, I can't tell how many significant digits that is. That could be 2 or it could be 4, because zeros, you don't know whether to count them or not. So I'm going to look at the way the book did the answer, and since the book rounded here, they're only counting 2 significant digits here. For these to be significant, they usually will indicate with a line or bar over one of those zeros to say if it's significant. They're not, so we assume just 2 significant digits here. So what we do then is round this, okay, to 8,000, and since we only have 2 significant digits, what you do is count 1, 2 digits. Look to the right, that's a 7. It's greater than 5, so we up the 2 to make it a 3. You're rounding up. And then because you need the other 2 digits there, you just put zeros in their place. So that's 8,300K. Now, if you recall, the surface temperature of the sun is quite a bit cooler than that. It was right around 5,800 K, if my memory's right. You can go back in the book and look at that. It's near 6,000 K is what it says. My memory is right around 5,800 is what they said. So this was a, whoops, one had to go out. Let me get them back. Okay. So what we have here is a star that's quite a bit hotter than the sun. In fact, if you go on that same page to table 14.2, you will see that 8,300K is right up there in the A range. We are a G star, that's a yellow star. That was a bluish star, 8,300K, very, very hot star. Okay? Now, the next example, a star emits light with a peak wavelength of 85,000 angstroms. That's a longer wavelength, but actually that produces a lower temperature because you're dividing by the wavelength. And you'll find out that's a 3.4 times 10 to the 3. So in other words, a 3400 K star, and that's down very cool star. That's down in the M range, a reddish star. So that's how you use that formula. Don't sweat it. I'm not going to be asking you to use that formula, but I did want to demonstrate it for you at least once. Okay, any questions on those? All right. Thank goodness I'm going to get out of this whiteboard. I hate writing on that, and you can see how terrible I write. And let's go back to our star types and go back to current slide. Now, for those who weren't here last time, I'm going to try to get this out of the way because this is right in the middle of my screen here. You can't see it, but I can, and it's blocking my view. Well, still that thing's blocking the view, so. All right, but it's going to fade out now, hopefully. What we had done last time, we talked about magnitude, the absolute magnitude of a star. Now, this is a little bizarre how they do this, but they do it. 0 is a really bright star, okay? The minus numbers are even brighter, okay? The positive numbers are less bright, okay? It's strange, but that's the way they do it, okay? So you have absolute magnitude this way, okay? That's on the vertical scale. If I can get can you see my arrow go up and down the scale? Can you see the arrow?
Yes.
Okay. That is the vertical scale. That's absolute magnitude. That's how bright the star really is from an equal distance from the Earth. Certainly our sun's brighter than any star out there, but that's because it's so close. But if you were to be able to position all the stars at equal distances, the brightest stars would be these and the dimmest stars down here. And here we're trying to let somebody back in. Miss Conwell, I believe it was. Yeah, Nakia is back in again, I think. Okay? I guess she had to go out. Okay. I'm trying to find, okay, got it. All right. Now, we just finished talking about temperature. Here's the temperature of the stars. Now, this scale is a little strange too, because they put the lowest temperature on the right-hand side and the highest temperature is on the left-hand side. So it's sort of a backward scale. That's because, well, it just fits that way better. Now, down here at the bottom, they have the representative groupings. The M stars are the coolest stars. That's why they're down here. The M8 stars are much cooler than the M0 stars. The K0 stars are hotter than the M stars. The G temperature stars, they're right down, that's where we live. That's our sun right there in the G range, okay? The F are a little bit hotter. The G's are the yellow stars. The M's are the red stars. The K is sort of the orange stars. G is the yellow stars. F is kind of the whitish stars. And then anything beyond that are bluish stars. The A's are not as hot as the B's, and the B's are not as hot as the O's. Now, the O's are very, very hot stars, very short-lived stars, very rare stars. You don't find that many O's, okay? And you'll see up here, there's just not many stars showing. Well, what does this diagram show? This isn't where these stars are in the sky. This is where they show up on the diagram. And most stars that are in the middle of their lifetime are called the main sequence stars. And they go in this little purple eel here that travels all the way across. There's very cool stars there, very dim stars there. There's average stars there like our sun, average in temperature, average in brightness. and there's very bright stars here, very hot stars here. And you see that in general, the brighter the stars are, the hotter the stars are in the main sequence here, okay? And that's what this represents. Now, we're going to learn later what these other groups are. Right now, they're just showing them to us. These are often called the giants or the red giants. And these are much bigger stars, but they tend to be, on average, cooler stars. I guarantee you back when this was in the main sequence, it was a hot, hot, hot star. Now it's much cooler. When this one was in the main sequence, it was a hotter star, but it was somewhere down here. Then you have the supergiants. These are also usually red stars, but these are incredibly large size, so that makes for a large magnitude. You see them easily, but they're still not usually, some of them are really, really hot still. And that's because we'll talk about why that's the case here. Now you have these down here. These are called the white dwarfs. Dwarfs because they're very low magnitude. It's hard to see them, though they have a pretty wide range of temperatures here. And we'll talk about why they're white dwarfs as well, okay? And explain why they're still pretty hot, even though they're low magnitude stars. So just get the grouping. These are your stars in their normal lifetime. These are called the main sequence stars here. There's probably a lot more of them than they have listed here, but they just fill up the space if you put them all. Some of the big stars that we recognize, and we'll see in the lab today, we'll recognize a couple of these. If I could get my key here. It keeps going out on me. You'll see these are high visibility stars, okay? And then we don't see many of these. We will see 2 of these in today, maybe 3 in today's lab when we do them. And then we won't see many of these at all because they're just really, really hard to see. These are low magnitude stars, below +10, which is above +10. You don't see those, okay? They're very hard to see without a telescope, a really strong telescope, by the way. I can't get my cursor back. All right, so there's the main sequence star. This diagram is called the Hertzsprung-Russell diagram. There's 2 more names if you want to write about people, a person. You can write about either one of those. You can write about how they developed the diagram, how they work together, how they work separately from each other, whatever you want to do on that. But that's the star types. All right, moving from that, and this is where we talk about these groups now, we talk about the life of a star. In the book, yeah, well, that's what it's called, Life of a Star. Now we go back to where we were way back at the beginning. And for those who weren't here before, we talked about some of this before, but this will be review for people who are here. For people who weren't here, you get to experience again. What protostar means is before it was a star. You might think this was pre-star, okay? Now, before it was a star, there was a mass of gases out there. Even in outer space, there are things out there. It's not all a complete vacuum. A mass, I mean a huge mass covering incredibly large areas of space. That's your nebula, okay? A mass of gases. Now, this is not yet a protostar, okay? It's a mass of gases. But something happens. And I'm not sure they know what happens. It could be some star explodes somewhere, and that sends vibrations and waves, compression waves, all through the atmosphere. And if this mass of gases that are out there, the gases get pushed together in that compression, and they start sticking to each other, now that's what they call gravitational collapse. Because what happens when the mass of gases get pushed together and they stick together, now their mass increases. When their mass increases, they pull more gas in. And when they pour more gas in, the pressure increases, the mass increases. The temperature increases because they're closer and closer and closer together. So this is called gravitational collapse. What happens when that happens is your density increases, your temperatures increase, and your pressures increase. All of those things are happening at once. You get more and more molecules or atoms of those gases pulled together. That creates a higher temperature. It creates higher pressure. Those temperatures keep going up, up, up until you reach about 10 million K. Now that is incredibly, incredibly hot. Now most of those gases, by the way, are hydrogen gas. And when hydrogen gas gets up to 10 million K, if I could get there it is, 10 million K, that's when fusion begins. They call it fusion ignition temperature. It's not igniting like igniting a fire. That's just when it's that hot, hydrogen that hot, it starts fusing to become helium. And boy, when that happens, it really gets hot, okay? The temperature goes up like crazy. And what's happening when the temperature goes up, it tends to expand, and the fusion tends to push things out, but the mass tends to pull it back in, and this is called a dynamical equilibrium. You have the inward force of gravity pulling things inward, and the outward pressure from the fusion energy, because it's exploding with a nuclear reaction, exploding outward, gravity pulling inward. That creates what they call this dynamical equilibrium. Now, when you pass this gravitational collapse and fusion actually begins, let me see if I'm saying that right. Somewhere in that phrase, that's when it becomes a protostar. The protostar is when it's past the point it's going to be a star. That mass of gases is not guaranteed ever to be a star. It's when it reaches the protostar stage, that's when it's no backing it down now, it's going to become a star. When it enters that dynamical equilibrium. And that's when it enters the main sequence. That purple snake that went down the middle. Okay? Now, whoa, that's not the key I wanted. Yuck. This is all the slides. Okay. Here we go. Let me make sure I didn't skip one note. All right. Here's what's happening. Gravitational collapse is pulling everything inward. This thing that you see on the slide here. There it is. Pulling inward. When this reaches 10 million K or so, and fusion begins to happen, now it's blowing. Okay, Bridget Cockrell is here. I think this is the first time she's been here this term. She was in class, I think, last term. Bridget, are you here? Bridget? I think she goes by Bridget. Bridget, can you hear me? Okay, I can't hear Bridget. Hopefully she can hear me. If y'all can tell if she's recognizing things. So here we are. Okay. The gravitational collapse has everything coming in. When that fusion happens, everything starts exploding out. It reaches this dynamical equilibrium. But before that, boy, it's a mess. I mean, explosions, collapsing, explosion, collapsing. Not a very stable situation. But when it gets stable, reaches that equilibrium, then now it becomes a main sequence star. Okay? So it balances out and becomes a main sequence star. And for some reason, I have to hit the screen again before it does. Okay. Now, what happens from that point? Okay? Now the star starts, and they call it tracing a path across the Hertzsprung-Russell diagram. They don't move anywhere. This is what's happening. Okay? When it becomes a star, a main sequence star from that last slide, once that happens, it's usually there. If it's a small star, it's going to be in that main sequence for trillions of years. If it's an average star like our sun, it'll be in that main sequence for billions of years. If it's a really big, massive, hot star, it's only going to be in that main sequence for a few million years. Long time, but much shorter than the other ones. Because we learned last time, and let me just go back and show you this. this is here. Nope. Sorry. I'll find it in a minute. Yes, here we have. The less massive stars have longer lifetimes. Those are the smaller stars. They live into the trillions of years. The more massive stars have shorter lifetimes. They only live for like millions of years. Our sun is an average star. It's right in the middle of its lifetime, we figure. It's about 5 billion years old, and they think it has enough fuel, hydrogen, left for another 5 billion years. I'm not going to worry about that. I probably won't be around that long. But at that point, it's probably going to start deteriorating. Okay? Now, that's what we're talking about now. What happens when it ends and gets out of the main sequence here? What is the deal? And that's what we're talking about here with stellar evolution. It traces its path across the HR diagram. It's in that main sequence. It hangs around there for millions, trillions, or billions of years. But at some point, no matter how big or how small the star is, you use up all the hydrogen in the core. Now, the core, remember, is that smaller part of the star. Star is way out here. The core is where the fusion takes place. And that's where the hydrogen is being converted to helium. Well, when that hydrogen is used up, there's no more fusion. So the core collapses. Remember, the fusion was what's pushing it out. The gravitational pull is keeping it in. When the fusion runs out, then it collapses because gravity takes over. There's no more fusion. So the core collapses. Uh-oh, it was already hot. When it collapses on itself, it heats up even more. So when it's heating up, the core is heating up, the outer shell expands and cools. Remember the outer shell. Now, for those who weren't here, I'm going to fly backwards just a moment here. Okay, sorry for y'all people who were here, but you might be able to use the review too. If you remember, yuck, I passed it. It was one of the intermediate waves here. Here we go. There's the core in the very middle down here. That's where all the fusion is going on. That's what collapsed on itself and got hot. Fusion started and it started blowing out. Okay? When it's dynamical equilibrium, the heat, the gravitational collapse is pushing inward, the fusion is pushing outward, and you have the star in the main sequence. Okay? But when all the fusion ends, then the core collapses and gets even hotter, and these gases out here in the outer shell, wait, I got to get somebody back in. Capri came back, so she was already here. These gases out here in the outer parts, they expand outward because they're cooling and moving outward because the core is getting hot and pushes them outward. So we have a collapsing core and an expanding circle. Now, for those who remember the very beginning, let me go back and see if I can find that again. Very, very beginning. There it is. That's what's happening right here. The core has collapsed into a tiny but incredibly hot, what they call white dwarf. White is very, very hot. Not as hot as blue, but very, very hot. Hotter than yellow, hotter than our sun. The core has collapsed and it's blown the outer shell, and those are the gases, and that's what they call the planetary nebula. Again, it's a mass of gases, but this time it's being blown outward, not being contracted inward. Okay, so we've seen that picture before. I wanted to tie it back together. Okay. All right. We're almost back. Okay, here we are. So the outer core collapse, the hydrogen in the core is exhausted. The inner core collapses, heats up to a very hot temperature, ultimately to be a white dwarf for many cases. The outer core shell expands because of that heat pushing it outward, but then cools. That's what forms your planetary nebula, which we saw before. Now, here again, here's where I was talking about before. The lifetime of the stars, those really, really, really big hot stars, massive stars, millions of years is all the life they've got. Those cool little red stars, they will hang around for trillions of years. Guess where we are? We are a G star right in the middle, and we hang around for billions of years. Okay? Our sun is what I'm talking about. The mass determines the ultimate fate of the star. These big, hot stars that don't last too long, more things happen after that core collapses. For the M stars and the cooler stars like ours, there's not too much left, but you'll see what happens. So that's where we're going next. Okay? Now here is the traces across the HR diagram. This is about where our sun was in that snow.